Okay, good day everyone. Okay, so we will have another example in our series shear and moment diagrams. Okay, oh, let us consider this type of beam. Okay, so as we can see, this beam has two overhangs, unlike the previous examples in which um, the spans are all simple spans. Okay, so here it will be a different scenario. Okay, so both sides has overhangs, and uh, it is a combination of a simple span and two overhangs on both sides. Okay, so let us try to draw each shear and moment diagrams. Okay, okay, so first of all, we need to draw we need to determine its reaction first in order to so that we can compute and we can construct its shear and moment diagram. Okay, so here, okay, so maybe okay, so let us say this is A and this is B. Okay, so since this is a pinned support, so it has um, a vertical and horizontal component, while this roller support has only vertical component, since it is a roller parallel to horizontal direction, so therefore it has no horizontal um, resistance. So for this pin support, it has AY and AX respectively, while only BY at this roller support. Okay, so let's try solving its reactions. Okay, so first we have summation of forces. Okay, X is equal to 0. Let's let us assume to the right as positive. Okay, so we have AX. Okay, since there's no other horizontal reaction, so we have AX is equal to 0. Then we need to sum up forces vertical or forces at y direction is equal to 0. Okay, so let us assume upward as positive. Okay, so we write first the horizontal and vertical reaction. So AY plus BY minus 10. Okay, since this is a triangle, so we have 1/2 BH. So 1/2 times 5 times 30 minus 25 is equal to 0. Okay, AY plus BY minus 10, 1/2 times 5 times 30 minus 75 minus 25 equals 0. So we have AY plus BY is equal to 110. Okay, so let us set aside this formula, and then we'll go to another equilibrium formula. Summation of moment equals 0. Okay, so let us choose which side to sum up moments with. Okay, so here I choose A. Okay, you can also choose B, it depends upon your situation. Okay, So let us consider, okay, so since we sum up moments at A, um, so here we set A as the fulcrum, and all the other forces will make this beam rotate, okay, relative to A. Okay, so this is your will be your fulcrum or steady point, okay, and the rest will rotate. So relative to this, okay, to point A, this 10 kilonewton force will tend to rotate, okay. Set this as a fulcrum, everything rotates, so this 10 kilonewton will tend to rotate, okay. uh, okay, so before I forgot, maybe we set a direction, what direction is positive or what rotation is positive. So I set counterclockwise as positive. So if A is the fulcrum, this 10 kilonewton will tend to rotate counterclockwise relative to A. So this 10 kilonewton will have a positive sign convention. So 10. And then relative to A, this 30 kilonewton distributed triangular load, okay, since this is its somewhere is its centroid, so this distributed load will move relatively clockwise, so it's negative, okay. Before I forgot, we must multiply this 10 kilonewton by its moment arm 1, okay. So we have 10 times 1 minus, okay, the area 1/2 times 5 times 30, okay, and the centroid of this triangle, okay, relative to A. So we have 5, okay, 1/3 times 5. Then relative to A, so this BY, okay, this is your fulcrum, and this and everything rotates, so your BY will rotate clockwise relative to A. So this BY is positive, has a positive convention, and you multiply it by the moment arm 5. Then from A, this 25 kilonewton will rotate clockwise, so this is negative. This is negative. And the moment arm of this 25 kilonewton is relative to A, okay, this is clockwise, so negative 25 times 6.5 equals 0, okay. Please be careful with how your sign convention, okay, or else you will get an erroneous answer, okay. So we'll compute BY. So we got 55.5 kilonewton upward as positive. Okay, since we got positive results, so therefore our assumption for the direction of BY is valid. So 55.5 kilonewton upward. Okay, and then okay. So I hope we got the correct answer. Okay, I will review. So, okay. So, we got the correct answer. So now, we're going to substitute this value to this equation. Okay. So, AY. So, we now have AY is equal to 110 minus 55.5. So, we have 54.5 kilonewton upward. Okay. So, this is okay. Then AX equals 0. Okay. So, I guess we have completed, okay, the values or all the values of the reactions. Okay, so we can now draw the shear and moment diagram. Okay, since this is triangular, so we cannot get, okay, so it would be in my own opinion, okay, so it would be easier so if we use shear and moment equations. For if only this is a rectangular distributed load, you can use what we have done in first example in part 2 of shear of our series. Okay, shear and moment equations part 2. Okay, you can use the method mentioned, okay, in that video. Okay, so I hope this is approximately straight. Okay, so we don't have a straight edge. So this will be your Vx for the shear diagram, and this will be your moment diagram. Okay, so since we have transferred all these values of the reactions in the drawing, so we may erase this one so that we can proceed. Okay, so we divide it into sections. Okay, so let us say this is section 1, section 2, and section 3. Okay, in which section 1, okay, we're gonna write its shear and moment equations. Okay, so from x equals to 0 to x is equal to 1. Okay, so we have this value. Ten kilonewton. Okay, so the shear here is obviously negative 10. So this will be the value. Okay, and then since it is downward, and then your moment is obviously negative 10x. Okay, 4-point load. Okay, so remember that our A, okay, so suppose we have negative p times x minus a for moment, but somehow the a is 0 since it started from the start. Okay, so x minus 0, so negative 10x. So this is your shear and moment diagram at section 1. And then we have section 2. This section 2 is from x equals to 1 to x equals 1 plus 5, 6. Okay. At that point, okay, we have this and we have this triangle. Okay, so let us draw it like this. Okay, so in which any random point 1 meter and then any random point x. Okay, okay. Okay, so since this is a reverse triangle that is downward, so let us convert it into which will result like this. Okay, so it should be increasing. Okay, so since this is decreasing, so we cannot use directly those formulas as mentioned here. Okay, so it should be increasing, not decreasing. So this triangular load, we should convert into two components. Okay, so it will be like this. Okay, minus, and then we have counteracting upward force. Okay, so that it will result to like this. Okay, so this will be a 30 kilonewton per meter downward force, downward downward rectangular force, and this will be 30 kilonewton meter per meter upward force. Okay, so this will be equivalent to this. Okay, 30 kilonewton. Okay, so just imagine. Okay, so this triangle is increasing and this 30 kilonewton load rectangular at the top is constantly steady distribution. This is increasing, so we can already apply the formula as written in these tables. Okay, okay, this is in our first video, shear and moment diagrams part 1. Okay, so this is what I discussed in that point. So we have V, so we have V is equal to, okay, so this is 10 kilonewton, 10, okay, minus, I know since this is downward, so it's negative 10 minus 30x, okay, minus, okay, minus our A here, okay, is 1. Okay, okay, so before we anything else, we have actually, okay, we have actually an upward force here. Okay, we have 54.5 kilonewton, which is AY. Okay, so let's conserve space. This is AY. Okay, so there is 30 and this is AY. Okay, so let us restart. So this is negative 10 kilonewton, and then we have plus 54.5. Then we have negative 30x, and then we have negative, okay, 30x minus 1, and then we have positive. Okay, so since this is upward, in order to its resultant distributed load would be like this. Okay, so this is 30x minus 1. Okay, it is squared over 2L. The 2L here is 2, and then the L is 5. So we have, okay, its equivalent would be negative 10. Okay, we have 44.5 minus 30x minus 1. Okay, then 30 divided by 10, 2 times 5, 10 plus equals plus 3 times x minus 1 squared. So this is your shear equation. Then for moment equation, okay, let us put it here. So your moment equation will be this downward force 10x minus, okay, let's put it negative 10x, then upward force plus 54 x minus 1. Okay, since its A is 1 meter away from the leftmost side, and then we have 30, we have minus 30, okay, times x minus 1 squared over 2. Okay, okay, and then we have 30. Okay, so we have negative w times x minus a cube over 6l. So the a is 1 and l is 5. So l is 5, 30. So we have plus, okay, 30 times x minus 1 cube over 6 times 5. 6 times 5 is 30. 30 over 30 is 1. Okay, so this is how you draw your moment diagram. Okay, so maybe let us compute, rewrite it directly. Okay, so that we can conserve space. So this is 15 times x minus 1 squared. Then we have 30 divided 30 is, so this will be plus x minus 1 cube. Okay, so this will be your moment equation. Okay, you can recheck that because your moment equation supposed to be is the integral of your shear. And then, so therefore, if you differentiate m with respect to x, you should get this value of v. Okay, at section 3, from x equals 6 to x equals to 7.5. Okay, so your V, so this time we can base in this bigger drawing, okay, so that we can conserve space. So we have V, okay, is the downward force, negative 10. Okay, so we have plus 54.5. Okay, so minus 1/2 5 times 30 plus 55.5. Okay, so we'll not include yet the last load, okay, see, because it's located at far end. So your V here is you add everything, so negative 10 plus 54.5 minus 0.5 times 5 times 30 plus 55.5. So we have 25. So this is your shear equation from 6 to 7.5 meters respectively. Okay? And then for moment, we have okay, for a moment we have, okay, negative 10 x, okay. So since there is no existing force between at section 3 in between this, so it is actually equivalent to this. So this is negative 10x plus 54 x minus 1 minus 15 x minus 1 squared, okay. But somehow there is an existing by 55.5, okay, so it will be an there will be an additional, okay, so x minus 1 cube, okay, the same as this, but there is 55.5, 50 plus 55.5 x, so this will be your moment equation. Okay, here that there 55, okay, x minus 1 cube, and this 55.5, okay, plus 55.5, there is an a, different a. The value of a is 5 plus 1, so times x minus 6. So this will be your moment equation. Okay, you can simplify this, but somehow you may or you may not simplify this. Okay, for me, I will not simplify this anymore, so that we will not okay, because there's no need, okay, so that we might find ourselves solving an erroneous equation, okay, using an erroneous equation to solve your shear and moment diagram. Okay, so maybe this is enough. Okay, so here at section 1, we'll concentrate first at the shear. So it is clear that your V should be is negative 10 from 0 to 1. So let us say this is a location where your force is negative 10. So this is, okay, so since this is the 0 line, so this is negative 10 kilonewton, and this is negative 10 kilonewton. And then our next, okay, this is our shear equation from x equals to 1 to x equals to 6. Okay, to make our efforts lesser, will go directly when x is equal to 1. Okay. So when x is equal to 1, it will be 44.5 this. Okay. 1 minus 1 and then 1 minus. So there is a straight line connecting. So this will be 44.5 kilonewton. And then since, okay, remember, so since this is a 1 degree curve, okay, remember in the first video, okay, what's the shape of its curve? So since this is, I know this is 2 degrees actually, this is 2 degrees, so this will be a 3 degree curve downward, okay, like this. Okay, so we just don't know how it will end at x equals 6. Okay, so let us solve the v when x equals to 6. So 44.5 minus 30 times 6 minus 1 plus 3 times 6 minus 1 squared. So negative 30.5. So it will end up like this. Okay, so maybe this is too much. This is just a very small value. So let us transfer this 10 kilonewton here lower. And this should be, okay, this should be like this. So this is negative 30.5 kilonewton, okay? Negative 30. Okay. So for section 3, this is the value of your shear, 25. Okay. So let us 25 until the end. So it will stay 25 until the end. But somehow there is a downward force 25 kilonewton. Okay. So 25 kilonewton upward minus 25 kilonewton downward. So it will be 0. It will still end up at 0. Okay. So therefore, we get our shear diagram. Okay. So next is the moment equation. We'll use moment equation. So when x is equal to 0, obviously m is 0. And when x equals to 1, our m, negative 10 times 1 is negative 10. Okay. So downward, negative 10 kilonewton meter. Okay. So next is this equation at section 2 from x equals to, from x equals to 1 to x equals to 6. So when x is equal to 1, obviously 1 minus 1, 1 minus 1, minus 1 minus 1 here. So it will be negative 10 still. Okay. So next thing we should do is here. Okay. So since there is a point in which the shear is 0, okay, we need to find this point x. Okay. So that in that area, we can compute the possible maximum moment. Okay. So it is located at section 2. So therefore, we equate this shear to 0. Okay. We'll find what value in which the shear is 0. Okay. And that value should fall between x equals to, between the values of 1 and 6 of x respectively. Okay. 44.5 minus 30 times alpha x minus 1, okay, plus 3 alpha x minus 1 squared, okay? So we equate this to 0 in order to find this value of x, okay? Okay? Say 5. So the value of x is 2.8. Okay, so let's use a lot of decimal place in order to be more accurate. 1148 meters. Okay, so in that area, so at this value, okay, we need to find its corresponding m. Okay, so its corresponding m. Okay, so this is actually what the calculator has computed. Okay, so at that value, we will use directly into this equation. Okay, so negative 10 times answer plus 54 answer minus 1 minus 15 answer minus 1 squared plus answer minus 1 to the power of 3. Okay, so we have computed 26.428. Okay, so since this is a 3-degree curve, so we will have a 4-degree curve here. Okay, so it will be a flatter one like this. We just don't know at what value speed it will end. So we have 26.428 kilonewton meter. Okay, so hope it's still seeable. Okay, so I just did not finish yet, okay, because we do not know what's the value when x equals 6. So the only thing is we substitute the value of we find m when x equals to 6 using this equation, moment equation at section 2. Okay, so negative 10 times 6 plus 54 times 6 minus 1 minus 15 times 6 minus 1 squared plus 6 minus 1 to the power of 3. So we have negative 40. Okay, so therefore okay, so we end up plunging to value of negative 40. Okay, so it will be like this. Okay, so I hope we did not get any erroneous answer. Okay, so lastly, we all know what value is x equals to 6. So what if x is equal to 7.5? Okay, we use this moment equation for section 3. And okay, and for that, since this is okay, since this is 0-degree curve, so it should end up like this. Okay, but we need to be sure that this will equate to 0. Okay, but since we have, okay, I guess this is exact, so it should be 0 exactly. So negative 10 times 7.5 plus 54 minus 1 minus 15 squared. Okay, plus Okay, so let's check this 6 times 5. Okay, -10. Okay, -40. Okay, so we can actually check if there's something wrong with our formula. Okay, so this is something wrong. Okay, this should be 54.5. Okay, and this should be 54.5. Okay, I'm sorry. So if that is the case, okay, okay, so so we have, okay, so this value, okay, so okay, so that's why we need to be extra careful when using shear and moment equations. Okay, so we might have forgotten a point. Okay, in this point this is 0.5. Okay, so I did not get 0 actually at beginning. It's 0.125, so there is a slight mistake. Okay, so we equate this again to 0. So it's like this. Okay, for shear equations at section 2. Okay, so it's exact, so let's substitute. Okay, so 2.8144. Okay, so we memory in this one, and then we substitute here. Okay, so this should be 27.333. See, this should be 27.333 here. Okay, so this is the maximum moment, and then okay, and then we determine what value when what is the value and when x equals to 6. Okay, so negative, okay, we have corrected this one. Okay, so -10 times 6 plus 54.5 times 6 minus 1 minus 15 times 6 minus 1. Okay, 5. That's plus, okay, okay, it's same. Okay, should be, this should be -37.5 kilonewton meter, and then this equation should equate to 0 when x equals 7.5. Okay, so -10 times 7.5 plus 54.5 times 7.5 minus 1 minus 15 times 7.5 minus 1 squared plus 7.5 minus 1 to the power of 3. Okay, plus 55.5 times 7.5 minus 6. Okay, okay, plus, okay, okay, so we get 0. So therefore, okay, so since you've got the values correctly, okay, so you can actually check. This is 25 kilonewton positive force times, okay, the area is 25 times 1.5 is negative 37.5, so it will end up at 0. Okay, so therefore this is now the solution. Okay, so this is your shear equation, and this is your moment equation. Okay, so next time, okay, when using shear and moment equations, we need to be extra careful. Okay, so just like we have experienced a while ago, we forgot to put 0.5. Okay, so that's why we did not get 0. But if you get the correct coefficients, so there is no point that you cannot get the correct answer. Okay, so that's it. Okay, so I hope you understand our lessons.